This is IB Chapter 18, Lesson H, 18H, and this is on definite integrals. Which, it seems to me, we've already talked about these a little bit, and but we haven't worked on evaluating them. So what we'll be doing is, so a while back we talked about the fundamental theorem of calculus. Which says that the integral from a to b of f of x, sorry, not big F, that comes next, is, and it would be the antiderivative of f at b, evaluated at b, minus the antiderivative of f evaluated at a. So the big F's are the antiderivatives. So now, when you find, so this is a definite integral, yeah, obviously. With definite integrals, you will not have the plus c, because you're actually going to find a value using this fundamental theorem of calculus. Also, I was looking, if you look in the book, there are a few properties, but they are properties that we already know. So I'm not going to take the time now to look at those. You can look on your own if you'd like. I think the best thing to do is just to jump right into an example, and then you can see how this works. So we'll skip on to the next page here. This is example 20. We're going to find the integral from 1 to 3 of x squared plus 2 dx. So the first thing to do is to find the antiderivative of x squared plus 2. And so by our power rule, we know that that's going to be x to the third over 3 plus 2x. And then we're going to be evaluating this from 1 to 3. And the way we write this is we put a bar and we put 1 down here and 3 up here. So please use the correct notation. Even if you're doing this in your head, please write this out. And then you write equals, and then if I had more room, I would write over here, but I have to come down a line. And then what we're going to be doing is we're going to be plugging 3 into the antiderivative, because this part right here is the antiderivative of x. So we're going to be finding f of 3 minus f of 1. So we'll simply put in 3 in for x. So I've substituted 3 into the antiderivative, and then it's always minus. And because I have a sum, I'm going to need parentheses, because I'm going to be subtracting the entire sum. And then I'll be plugging in 1 for x. I'm just going to write this out so you can see what I'm doing. And then it's just a matter of simplifying it. So 3 cubed is 27. 27 divided by 3 is 9. Plus 6 minus parenthesis 1/3 plus 2. And we could go ahead and do 9 plus 6. 1/3 plus 2 is 2 1/3, which is going to be 7/3. And we might as well get a common denominator and work this out. So we've got 45/3 minus 7/3, which is 38/3. And that's it. So that's the area. It would be the area under that curve from 1 to 3 as well. That's what this value would tell us. It's also known as the definite integral. Next. So we're just going to keep doing a couple of examples. Letter A. The integral from 0 to pi over 3 of sine of x dx. Okay, first thing we do, we take the antiderivative of sine, and we were working with this the other day. It is negative cosine, right? And then we're going to evaluate that from 0 to pi over 3. So we write it like this, equals, and then we're going to have negative cosine of pi over 3 minus negative, so that turns to a plus, cosine of 0 equals pi over 3. You can use your hand. Let's see. I'm trying to think, do I want to do it with the hand or what? I'm going to do it with the hand. So pi over 3, that's up here, cosine's 1. So it's 1/2. It's negative. And then cosine of 0 on the unit circle would be 1. See, this is one of those cases where the cosine of 0 is not 0, it's actually 1. And then negative 1/2 plus 1 is 1/2. So that's the answer to that one, and then we'll move on and do the next one. Again, please write all your work out, especially this big step right here, so I can see your entire setup. I want to see all of that. Integral from 1 to 4 of 2x plus 3 over x dx. So, same old thing. Take the antiderivative of 2x, which is going to be x squared. And then the antiderivative of 3 over x. Think for a sec on that one. The 3 is going to be a constant, and the integral of 1 over x dx is the natural log of x in absolute value. From, and all that's evaluated from 1 to 4. In this case, we don't really need the absolute values because 1 and 4 are both positive. Anyway, plugging 4 in, 4 squared is 16, plus 3 times the natural log of 4, minus, parenthesis, because I have a sum. Plugging 1 in, I'm going to get 1 squared, or 1, plus 3 times the natural log of 1. Now, the natural log of 1 is 0, so that's going to just be 1 there. 16 plus 3 natural log of 4 minus 1. So 16 minus 1, 15 plus 3 natural log of 4 is our answer. Now I'm looking at the book. They wrote theirs differently. So, yes, sometimes that happens. What they wrote is they wrote 15 plus 6 natural log of 2. Is there a way to reconcile these two answers? Well, there just might be, because we can use some properties. 4 can be written as 2 squared, and then we can bring the 2 out front to the multiply to the 3, and we get 6 natural log of 2. So, the book is actually correct. They did not make a mistake, they just rewrote it. And I am happy with either answer, either version on our classroom tests. And I honestly don't know if the IB would, if they have a preference for one or the other. I don't know that. I'm guessing they're going to be happy with this one. I would hope so. And believe it or not, we only have one more example. This is a pretty sweet short section. Evaluate from 2 to 5 x e to the x dx. And it says accurate to 4 significant figures. Be careful there that it's not 4 decimal places, it's 4 sig figs. So just be watching. And I'm just looking, I'm noticing, of course, the book they did with their calculator. If you were to try to do this by hand, would you be able to with what we know? Let's try it just for fun. So you could probably recognize that this is a product, obviously, x times e to the x. So you are not allowed to, or it's not going to work to integrate x and integrate e to the x individually because they're not a sum, they're a product. So the only technique that we know is u substitution. So you would have to choose a u, and the logical u, in my opinion, would be, well, I guess x. Because, and you're not going to get very far with this, because if you do du, you're just going to get dx. And if you tried to substitute this, well, what would happen is you'd have the integral, you would replace the x is u, you'd have e to the u, and then dx is du. And guess what? You have the same exact thing. You didn't get anywhere with that. It turns out there is a technique for this. It's called integration by parts, but IB doesn't cover that. So in this particular case, we will do it on our calculator because we get stuck if we try to do it by hand. On an IB exam, they would have to tell you use a calculator so that you make sure you don't try to do it by hand. Okay, well anyway, let's bring that calculator up. Clear. We can just go to a blank screen. And I can't recall if we've done these before in this class or not, so bear with me. Having both the AP and the IB, I have to ask whether we've covered these things because I can't remember which one has done what. So it's math 9, press the math and then 9 to get f int. And if you're on an 84, it's going to look like the integral. If you're on an 83, then this is what you type in. You type in the integrand, x e to the x. And then you have to do a comma, and then x, because that's the variable, comma, and then your lower bound, comma, and then your upper bound. And then you can hit enter, and it will give you the value. And it's supposed to be accurate to 4 sig figs, so that means it's going to be 586.3. I'll bring that back up so you can see it. So let me write the notation here. It's f int, the function, x, the lower limit, the upper limit, or the upper bound if you want to call it that. And that concludes the lesson.